Justin Miller, Abstract College Physics here. We are going to keep on going with electric fields. We looked at some continuous charge distributions, not electric fields yet, but that's what we're going to do. What's the electric field due to a continuous charge distribution? Well, that depends on where you want to know it, right? Where do you want to know it? What sort of charge distribution do we have? Is it a nice linear charge distribution? Is it an area or surface charge density distribution? Volume charge? How is it laid out in space? So we're going to start off with simple cases, simple-ish cases, and we're just going to say, hey, the electric field due to a continuous charge distribution. Well, the electric field in terms of its magnitude is going to be equal to, let's say the absolute value because we're just talking about magnitude here, of K sub E dq over r squared. And of course we've got dq there, right? So whoosh, we need to be integrating absolute value of that integral there. So it depends. The magnitude of the electric field depends on the charge distribution dq and how it's laid out spatially. So what we want to deal with in this particular case is start off with something nice. Let us consider a line charge, continuous, with a uniform line charge density lambda. So uniform, we're saying that it's constant, it's not varying spatially. So we're just going to take ourselves a line. Whoosh. Let's say this line has some length L and has some uniform charge density lambda, which is its total charge divided by its length. And we want to know, what's the electric field due to it? Well, in order to answer that question, we have to be more specific. Like, where do you want to know what the electric field is, right? Because all over in space, there's an electric field that has a magnitude and direction due to this line charge. So we've got to be more specific. So we're going to start off with the simplest case, and that is, well, what if we're aligned with one of the ends? So what is E hat at a point aligned with an end of the line? So aligned with the ends, there's really two different sides that we could be on. We could be aligned over on this side, or we could be aligned over on this side. I'm just going to take the latter, and it doesn't really matter, but we're going to say something like, hey, what's E hat there? Or we could again do it on this side as well, but aligned with an end. Well, we got to draw out some other things in order to understand what we've got going on here. So we've got the length of this line charge. It's some length L, that's great. And that terminates there. And then we have that this point is some distance away from this end. So we could put that in as some distance as well and say that this is some distance. This pin's a little dull, but that's okay. Or some distance away from the end. And that's where we want to determine what is the electric field. So right here we've only got the magnitude. Why are we only dealing with magnitude there? Because the direction depends on a couple things. It depends on where we are and what sort of line charge we have. Is it a positive line charge or is it a negative line charge? Are we on the right side or the left side, or if it's flipped around, are we above it or below it? So let's think about, for this particular case, we'll make sure that we're putting in plus lambda so it is a positive line charge density. So we can think of this as a bunch of positive charges that is just spread out uniformly across this line, and we have a net positive charge, some total charge, and that's it. We know what the electric field is here. So what direction do you think the electric field would be in at this location if this were a big line of, well, a positive charge distribution? Well, we've got every infinitesimal, every dq would have a radially outward directed electric field relative to it. So we can take a little dq right here and say, well, radially outward with respect to this point is that way. With respect to this point is that way. With respect to this point is that way. Anywhere we look, the radially outward with respect to that dq, or that line element dl, is going to be radially outward, and aligned with the end is going to be in that direction. So we should note that the electric field here, just by directed inspection, has to be in the I hat direction. Now if we're over on this side, radially outward with respect to all the elements would be that way, and we'd have negative I hat. Or if this were a negative line charge density, we'd have radially inward. If this happened to be negative lambda, well, every contribution would be negative, would be radially inward, which would be in the negative I hat direction on this side, and positive I hat direction on this side. So again, you have to be aware. What side are you on, and what type of line charge density are we talking about, positive or negative? So if this is positive, radially outward, there we go. So we've already got the direction. Okay, we already know what direction the electric field is going to be in. So this is all that's left, is to figure out what the magnitude of it is. Great. So you can just note that it's in the plus I hat direction. Check. So we're left with the magnitude. So how are we going to get the magnitude? Well, again, we've got to integrate over this charge distribution relative to the point that we're trying to deduce what the electric field is. So every little element, line element here, is some radial distance away from this point. And as we integrate over this, we should note that, well, this point here is a distance a away from this, and this point here, this end, is a distance of L plus A away from the point where we're trying to determine the electric field. Again, that's what this R value is, the radial distance away from the point under consideration, or the infinitesimal under consideration, of which we're trying to determine the electric field due to it. So we note that R is varying, right? R is going to vary from a distance of L plus A to a distance of A. So that has to do with our limits of integration then. We want to integrate over the total charge distribution. And, well, R is, again, the radial distance away that we're integrating over. And we got this dq to deal with. Well, dq, as we've already said, is lambda dl. Lambda dl because we're just dealing, again, with a line charge here. It's a one-dimensional lambda dl. Well, there's L right there. So we split this up into a bunch of infinitesimal line segments. We've got lambda dl. Boom, there we go. That's what we've got to work with. So let us go ahead and take this and go ahead and apply that. So for this particular scenario, we've got the magnitude of the electric field at that point P. So we can call this some point P there. At P is going to be equal to absolute value of the integral. Now we're going to put k sub e times lambda dl divided by r squared. And we note that the radial distance, once again, is going to vary from L plus A down to L. So our limits of integration should be like that. Well, we could fix this up a little bit, change some things around to make it a little bit more convenient. And the way that we could do that is we could kind of go ahead and say, you know what, let's just embed this on a Cartesian coordinate system. We've got, hey, there's the x direction, there's the y direction, and we'll lay this line charge along the x-axis. Why do we want to do that? Well, because then we can talk about things a little bit easier. Instead of some dl, now we can talk about dx. And instead of r, we can talk about just some distance x. So when we do that, it's a little bit more convenient. We can say that, well, dl has to be equal then to dx now, and r is equal to x, some distance away from that point. That's it. It's all in x. So what does this do for us? Well, now we've got ourselves that this goes to the magnitude of e hat at the point P is equal to the absolute value, forgot to close that, absolute value of the integral from L plus A to A times k sub e lambda dx over x squared. And there we go, look at that. Now that's a pretty easy integral to solve because lambda and k sub e are both constants. So what do? We go ahead and do this, right? And what do we get out of this? Well, let's rewrite it. We've got ourselves that pull out the lambda and k sub e, both are positive quantities, so that's good. If lambda happened to be negative, we'd have to be a little bit more careful of that because it's the absolute value of the whole thing, but it's positive, we'll just pull it out. And then we just got ourselves the integral from L plus A, or from A to L plus A of dx over x squared. Whew. What do we get out of that? Well, what's the integral of 1 over x squared? Negative 1 over x to the negative 1. That's it. So, still have the absolute value signs there. And we get ourselves, this is going to be equal to k sub e times lambda multiplied by the absolute value of negative 1 over x. Let me put the absolute value out, the whole thing, so this doesn't get confused. Evaluated from a to L plus a, close the absolute value. Didn't really need to take that out, we can keep it in. It's probably for the best, in case lambda is negative. Anyways, this is what we've got. We can go ahead then and evaluate this over these limits. So we've got ourselves k sub e times lambda, an absolute value. And then we've got ourselves negative 1 over L plus A minus negative 1 over A. Close absolute value. Good. And then what can we do with this? We can kind of mess around with it a little bit. So we've got that this is the absolute value of k sub e times lambda. Then we've got this term ends up to be positive, this one's negative, so let us just switch the order of that and say that this is just as well equal to 1 over a minus 1 over L plus a. And what can we do with that? Well, if we can get a common denominator between those two other terms, we'll say that this then is equal to k sub e times lambda multiplied by L plus a divided by a times L plus a. Good. And then we do the same thing for the other side. We've got a divided by a times L plus a. Close absolute value. And this is going to be equal to the absolute value of k sub e times lambda. And what do we get? Common denominator here. So we've got L plus a minus a divided by the quantity of a times L plus a. So the a minus a goes away, and we are left with, this is multiplied by L divided by a times L plus a. Grand. So what can we write? All said, well, L's a positive value, A's a positive value. Those are just distances away from the far end and the near end, or excuse me, the length of the line and the distance from the near end. K sub e, that's positive, lambda's positive. So all these quantities are positive here, so we can drop the absolute value, don't really need it anymore. And we've got ourselves k sub e, lambda L over a times L plus a. There's the magnitude of the electric field, a distance a away from the end of a uniform line charge that has a length L and a line charge density of lambda. We've got ourselves a nice formula here, derived for a specific situation, but this is utilizable anytime we've got a line charge and we're looking at the electric field magnitude when we're aligned with one of the ends. That's it. So in the end, for this particular scenario here, we've got ourselves that E hat at the point P is just equal to, case of E, lambda times L over A times L plus A, and this is in the positive I hat direction because again, radially outward with respect to the line's orientation is positive X. And boom, that's what we get. There's one other way that we could write this, and you may see it from time to time, but what is lambda times L? Well, let's see. Lambda itself, because lambda is constant, lambda is going to be equal to the total charge divided by the length. So we have that lambda times L is equal to Q. We could put Q total here. Q total. And that's the total charge that is encompassed within this line itself. It's uniformly spread out. That's great. So another way that we could write this electric field out is say that E hat at P is equal to case of E times Q total divided by A times L plus A. And in this case, again, I hat direction. Magnitude, that's going to go for anything, any line charge we're aligned with an end. The direction, again, that's going to be gotten by considering where you are relative to the line charge, what side of it you're on, and whether it's a positive or negative line charge density. All right, so that's a nice, nice formula. That's the end result for the magnitude. All right, so, yeah, let us do another point around this line charge. Those are very specific points. We'll do another one that's specific too, but whole different scenario. Let me erase this up, be right back, and we will do that. 1 second. Alrighty, so what do we want to do? Well, this is what we want now. We're going to take another line charge. It's supposed to be a straight line. We'll assume that it is. And instead of looking at the electric field aligned with an end of this line, we're going to look at what the electric field is at a point that's aligned with the midpoint. So, not with an end, with a midpoint. So we'll say like right here, midpoint. And we'll talk about, hey, what is the electric field? There. So in this case, we've got the electric field due to a continuous line charge at a point aligned with its midpoint. So in this orientation, that would either be above or below. If the line was like this, it'd be to the left or the right. We could have the line in a diagonal, but it's 90 degrees with respect to the plane of the line, or the line of the line, and aligned with the midpoint. So there we go. We want to know what the electric field is. So we'll just go ahead and say, hey, we've got ourselves another plus lambda here. We'll talk about if it's negative. What else do we have? Well, we could go ahead and say that this position right here, this point, which we could call point, put it on this side, point P, is some distance A away from the midpoint. Great. We could say that this line charge has some length L. I guess that would be okay too, because it does still have some length L. And what do we want to know? Again, we want to know how everything adds together. We have all of these little line segments that have some dq within them that all have some contribution to the overall electric field at that position in space. And we want to know what that is. So I'm going to do this in a couple steps to try to get the idea of what we're looking at here, and then we'll proceed to unravel this and figure it out. So first off, consider not a line charge. Say if a collection's point charges were symmetric about the center of the line they are arranged in. We would have whoosh, this. So we're going to take that continuous line charge and just think for a second about a collection of point charges that's evenly distributed on either side of some midpoint. So we can take that there is some Q1, some Q2, we'll just do it for a few, Q3, Q4, and Q5. And we'll say that all of these charges are the same, 1, 2, 3, 4, 5, they all have the same amount of Q. So we'll just call this Q1, Q2, Q3, Q4, Q5, and Q1 through 5 equals the same charge. And then we'll say that they're all evenly spaced by the same distance, which we could call like just some distance. What do you want to call it? How about we call it a distance, I don't want to call it L or A, so I'm just going to call it a distance X. X, 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 X. So that everything's symmetric about this middle charge, which is Q3. Same amount on the right as on the left, everything's equally spaced relative to it. And then we go ahead and we go up some distance from this charge, and we say, here's the point P that we want to know what the electric field is. What's the electric field at that point? Net electric field. We say, hey, we got to sum up the individual electric fields from these individual 5 charges. I say, yeah, that's right. That's all that we got to do. So let's kind of take a look at how that looks itself. So we've got this Q1. Well, Q1 is some distance away, which we could say is R1. So I'm going to go like this. And say that that's some distance R1. And we're again going to assume that these charges are all positive, such that they all produce radially outward directed fields at the location. So radially outward is in this direction. And that would be like our E hat 1. Fantastic. So there's the electric field due to just that one charge there. We've also got the electric field due to this charge here. So this charge is some distance away, which I could call some R2, and its electric field would be more like this. E hat 2. It's not pointing in the same direction, right? Heck no, it's not. And then we've got this one, well, that points directly above it. We've got this is some distance, which we'll just call R3 for the sake of argument here. And the electric field would be, in this case, E hat 3. Notice I'm making the magnitudes bigger because as we get closer to this charge, we're getting closer to this point. And again, the magnitude's inversely proportional to the distance away squared. So these are the electric field vectors due to these 3 charges, in a sense. And if we wanted just the net electric field due to just this side, we just add those up. That's great. But we've got the other side too. So what happens with this other side? Well, this one is some distance away, which is going to be R4. But R4, if these are the same distance away from this charge, this is equivalent R4 is equal to R2, so it's the same distance away, it's the same charge, so it'll have the same magnitude of the electric field, right? So we've got like magnitudes, and then its direction will be like this. There's E4, okay, and then we can come over here to this E5. Oh, this is going to be some distance away, R5, which is going to be the same distance away as R1. R5 is equal to R1, and its direction is going to be this. So what do we get out of this? Why bother with this? Well, we bother with this because there is something that we can utilize in this particular scenario to greatly reduce the amount of work that we have to do. And it's something that becomes very important in general, and that is symmetry. We could use symmetry arguments to sort of figure out what direction the electric field has to be at that point. And that will lead us in a way of simplifying what we have to do in order to produce or determine what the net electric field is there. So notice this. The magnitude of E5 is equal to the magnitude of E1 because they're the same distance away and we're talking about the same charges. And the magnitude of E4 is equal to the magnitude of E2. Just as well because E4 and E2 are the same distances away from that point, and E2 and E4 have the same amount of charge being considered. So we've got equal magnitudes on either side regarding E1, 2, 4, and 5. What about the directions? Well, what do we have here? If I go ahead and draw like an axis there, I can draw in like an E1. And I can also draw in, that shouldn't be E1, that should be E5. E5, and I can also draw in E1. Because these two charges are the same distances away, the angles that they make with respect to the y direction are going to be the same. We got some theta 1, and we've got some theta 5 relative to the y direction there, and theta 1 is equal to theta 5. And we'd have the same thing for theta 4 and theta 2. And theta 2 is equal to theta 4. Well, what happens then? Well, if we look at the x components of these two vectors, this one has an E5x, and this one has an E1x. Equal magnitudes, but opposite directions. E1x is equal to negative E5x. So what happens? The x components cancel out. Just as much on this side as is on this side, x components cancel out, which just leaves us with the y components of both of these. Y components are the same. We have E1y is equal to E5y. So when we talk about the net electric field of adding together E1 and E5, it's just 2 times the magnitude of the other, 2 times the magnitude of one of them in the j-hat direction, because the x components cancel each other out. And we have the same thing that would happen between E2 and E4. It's only the y components that survive when we add them together. That is to say that all of the x components in this scenario here go away, which leaves us with an electric field that must be pointing straight up. Only the y component survives. And that again is because of symmetry, because we have just as much on this side as on this side, and everything's equally spaced. So overall, by symmetry, no x components survive. Not like it's a war and they're fighting each other, but we're only left with a j-hat component in this particular orientation. Well, what can we do with this? Why did we consider point charges when we're considering a continuous line charge? Well, if we're directly aligned with the midpoint, we have just as much on this side as we do on this side. They're not points, but we can still think of them as infinitesimal elements that we're going to integrate over and add up the overall effect. So this end here has an electric field this way, and as I sweep across this way, that electric field sweeps across to this direction. And then I integrate over this part, and the electric field sweeps across that way. The x components are all going to be equal and opposite regarding the two other sides. This side and this side, which is only going to leave us with j hat components that survive. So when we go ahead and start thinking about adding together all these vectors, this simplifies things greatly because we don't have to worry about the variance in the directions of the vectors because they cancel each other out in one of the dimensions. We're only left with one. So if we are able to extract out the y components of all these vectors and add them together through integration, we're good. That's exactly what we want to do. That still takes a little bit of work because, well, what do we have? We have that the distance away, this r value, varies as, again, as we sweep towards the midpoint. Okay, so r is varying. And yeah, the angle that these vectors are pointed at is varying, which varies then the y component of it as well. So those are some things that we got to be a little bit careful of. But we'll set up some coherent way of figuring this all out, and we will go from there. All right, so first off, by symmetry, because we're going to have equal amounts from either side in the y direction in this case, we only have to do one side. And then 2 times the electric field from one side will be the total electric field. By symmetry, we need only to determine the net E hat field in the y direction due to one side of the line relative to the midpoint. Net field due to the entire line will be 2 times the value from one side. And look at how I just kind of snuck that in. Ooh. That's from something else. So yeah, a little bit messy, sorry about that, but I'm trying to conserve space a little bit. So let us consider this then. If we just get the electric field from one side of this distribution and we just double it, we know that there's only a y component anyway, and we've got the total magnitude of the electric field at that point. And moreover, we know that it has to be in the positive j hat direction if this is a positive line charge density and we're looking above it. If we're looking below it, that would be in the negative j hat direction. If it were a negative line charge density, everything would be radially inward. Still, all the x components would cancel out, and we'd have negative j hat or positive j hat if we're below it. So again, we still got to be aware of what side are we on and what sort of line charge density do we have. But that's pretty easy to keep track of. But it's something you got to think about, right? Can't just say, oh, this is just a bunch of math. We'll just put in some numbers and we're done. Think about it. Think about it. All right. So at any rate, we should note that E hat total is in the J hat direction. All the x components cancel out. So now it's a matter of getting that, right? Whew. So let us just consider half of the distribution now. So like this. Say that we are looking at the distance A, so this would be the midpoint. We're kind of ignoring the other side of the distribution right now. Here's the point P in which we're trying to determine the electric field due to this particular portion. And this would have a length, which would now be L divided by 2, cut it in half in a sense, and does have some uniform line charge density, which we're considering to be positive, and it is a lambda. So we just want the magnitude. How are we going to get the magnitude? Well, every point here has some angle that it makes relative to that particular direction, right? So we could say that there's some angle here, phi. And we're going from that phi, let's call it phi 0. We're going from phi 0 and, well, eventually phi goes to 90 degrees. Well, maybe we do something else, right? Excuse me, it'd go to 0 degrees. Let us, instead of looking at phi, we're going to look at this. Because we know from this endpoint right here, the electric field due to it would be in that direction, right? And what do we want to get out of this? We want to get the y component out of this. Because the x component is irrelevant. We can ignore it. We don't care about the x component. So we want to get this y component. The y component looks like that. So E sub y relative to this little dq right there. So we could say that we got some dE sub x and dE sub y. Excuse me, this is just dE due to that little element right there. So what do we got? How are we going to get the y component out of this? Well, we could definitely say that we're looking at utilizing the sine of this angle. That would be okay because that would stretch out that way. But we could also start looking at this angle right here, the angle between these two vectors. Let's call that theta sub 0. And notice that as we sweep over this way, those two angles become aligned because this matches up with that direction. And that angle there is this same angle right there. And moreover, if we take the cosine of this angle and multiply it by this dE, we've got ourselves the y component. That's pretty cool, huh? So, what do we have out of this? We've got ourselves the ability to extract out the y component and say that dE sub y is going to be equal to dE times the cosine of a theta. And that is completely in general, where dE is the magnitude, the infinitesimal element of the magnitude due to this infinitesimal point right here. So that might look a little bit odd, but just consider this is a point charge. That would be the electric field due to the point charge. If we want the electric field only in the y direction due to this portion, or this overall electric field, we take the magnitude of it, multiply it by the cosine of theta sub 0, and we've got it. Well, theta is going to actually be changing as we sweep across. This theta sub 0 is just the largest angle. We're going to go from theta sub 0 down to 0 as we approach this line. And it's easier, in my opinion, to think of integrating over theta this way and sweeping along, instead of integrating over the line charge distribution with this theta. That seems a little bit awkward to me. Though it's still doable, and you use sine instead of cosine, but we're going to use this thing. So, what do we get? Well, let us first write out what this all looks like. We've got the magnitude of the electric field at the point P is going to be equal to the absolute value of the integral of k sub e dq over r squared. So there's the magnitude of the electric field. And again, that's just completely in general. We haven't put any limits of integration. We haven't really defined what is R and what is dq. Well, we already know that dq is equal to lambda dl. Yeah, that's it. And we can figure out some way of dealing with r, and then we can figure out some way of dealing with all of this. So this would be the overall magnitude due to, well, integrating over the entire distribution gives us the entire thing. But we just want the y component. So if we look at what is the magnitude of the y component at p, what do? Well, we take this whole thing and we multiply it by the factor that we need to just extract out the y component. That's it. So we could have now the integral of k sub e dq over r squared times the cosine of phi. Excuse me, cosine of theta. That's what we're calling that one. Yes, cosine of theta. Boom. So we're on our way to start to set things up, extracting out just the y component with this cosine theta. So what do we have here? Well, again, we've got the dq can be written as lambda dl. That's fine. If we go ahead and say, you know what, let's just put this on an x-axis and say that's along the x direction. We have that dl goes to dx, so this is equivalent to lambda dx here. That's good. What about r? Well, r is r. R is this distance right here, which again varies. So we're varying a couple things right here. X varies as we sweep across. The angle theta varies as we sweep across. And the radial distance away varies as we sweep across this line distribution relative to that point in the integration. So we've got three things that are varying here. X, r, and theta. Well, this is a single integral. We got to figure out what we want to integrate over and just see if we can write everything else in terms of that. And we could make everything in r, or make everything in x, or make everything in theta. And the latter turns out to be the easier of the three, in my opinion. But let's just go ahead and do it, right? All right, so let's see here. I need to erase stuff. Yeah, I think I'll have to do a little erasing here. Keep that up there. And this. So, we've got three different things varying, but they're all interrelated with each other. And we just got to find the relations between them in terms of the variances so that we can write this all out as one nice expression. So let us do something like this. We've got this nice triangle here. We've got an r, we've got a theta, and we've got an x, and we've got an a. Well, how could we write, say, r in terms of theta and another constant? A is just a constant, the distance that we are away from it. That should be easy. We could look at this and say, oh, well, the cosine of theta is equal to adjacent over hypotenuse, which would be a over r. So the cosine of theta is equal to a over r. So we could write out that r itself is equal to a divided by the cosine of theta, which then says that our value r squared there in terms of its variance with respect to theta can be written as a squared divided by cosine squared theta. All right, so we've got the r taken care of. What about x? We want to keep x, or do we want to get rid of it? Let's get rid of it. Let's rewrite x in terms of a theta as well. Well, before we do that, let me stick this in here and see what we're doing. We've got the magnitude of e sub y at the point P is going to be equal to the integral of k sub e lambda dx cosine of theta, divided by r squared, or we just said that r squared can be written as a squared over cosine squared theta. Absolute value, kabam. So we don't need x, we need dx, but we can still get a representation of how this works out Because, again, we want it in terms of theta. A is a constant, and we can say that from this, the tangent of theta is opposite over adjacent, right? So we've got the tangent of theta is equal to x over a, which gives us then that x is equal to a times the tangent of theta. What about dx then? Well, dx by d theta is equal to d by d theta of a times the tangent of theta. All right, so there we have the rate at which x varies with respect to theta, and how it correlates back with this representation here. So what do we get? We've got the dx d theta is equal to, what's d by d theta of the tangent of theta? A is just a constant. Yeah, it's secant squared theta. So we got that this is equal to a times secant squared theta. And thus when we solve this out for dx, multiply both sides by d theta, and we've got that dx is equal to a times the secant squared of theta d theta. Bam! That is a fantastic. So what do we want to do with this? Yeah, we want to go ahead and start putting that in for dx and see how this all comes into light. So we've got the electric field at point P, again, this is due to half of the distribution, is equal to the integral of, we've got a k sub e, we've got a lambda, we've got a cosine theta there, and then we've got another cosine squared theta. Whew, let's go ahead and write that as cosine cubed theta. And then we've got ourselves the dx. Well, what's dx? Dx is a times the secant squared of theta d theta. So we've got an a times the secant squared of theta d theta. And then we've got that this is all divided by a squared. You may look at that and go, oh shoot, that looks a little bit not too friendly. But it actually is. It actually is really nice. Very nice at that. So what do we do with this? Well, one thing, we need some limits of integration, right? What are we integrating over? We're integrating over theta now. The only thing that has variance in here is theta, right there. So that's what we're integrating over, so we need our limits of integration. So what are we going to integrate from? Well, we integrate from the largest angle relative to the midpoint down to 0. That's it. When this goes down, it goes across the entire distribution, or half of it, and we're down to 0. So we can have our limits of integration go from 0 to theta sub 0. Theta sub 0, again, is the large angle with respect to the end of the distribution. So what do we get out of this? Well, a factor of a cancels out down here. That's great. K sub e and lambda, those are just constants. And then we've got cosine cubed theta times secant squared theta. What's secant? That's right, secant's 1 over cosine. So secant squared is 1 over cosine squared theta. So we've got cosine cubed theta divided by cosine squared theta. It's just cosine theta. Whew, that was a mouthful. But this is what it all reduces down into. We've got the magnitude of e sub y at the point P due to half the distribution is equal to the integral from 0 to theta sub 0 of k sub e lambda divided by a times the cosine of theta d theta. Again, this is just a constant. Whoa, that looks pretty easy all of a sudden, right? Now you just have to integrate the cosine of theta. Wow, that's pretty simple. So let us come back over to here. I'll erase this part right here. And we'll just do that. So we've got ourselves k sub e lambda a. What's the integral of cosine theta? Whew. Integral of cosine theta is sine theta. That's right. So we've got ourselves that the magnitude of e sub y at the point P due to 1/2, this is due to L over 2, is equal to the absolute value of k sub e lambda divided by a times the sine of theta evaluated from 0 to theta sub 0. and absolute value. All right, well, we just evaluate this over the limits of integration. What's the sign of 0? 0, that's right. What's the sign of theta sub 0? It's the sign of theta sub 0. So in the end, due to this half distribution, we've got ourselves that the magnitude of E sub y is going to be equal to k sub e lambda times the sine of theta sub 0 divided by a. And theta sub 0 is some angle between 0 and 90 degrees here. Boom, which is positive. Well, that's pretty fantastic, right? That's half the distribution though. We want the whole distribution. Well, the whole distribution for the entire line the magnitude of E hat total is equal to 2 times the magnitude of E sub y at P due to L over 2 due to half the distribution. And this is again at P, we should say E sub y. There we go. So what do we get out of this? We've got that the magnitude of the electric field itself, x components all go away now because we don't care about them anymore. Once we add in the second half, all the x components cancel out. We've got the magnitude of the electric field at P due to the entire line is equal to k sub e lambda divided by a times the sine of theta sub 0. And if we wanted to go ahead and say what direction is it in this particular case, we got that it is in the positive j hat direction. So I'm going to put positive j hat here. Because again, we're above the line, it's a positive distribution. And there we go. It is the direction. So anytime we're talking about what the electric field is at a point aligned with the midpoint of a line charge of continuous and uniform line charge density, boom, all we got to know is what is the line charge density and how far away are we from the midpoint for getting the magnitude, and what is the angle made with respect to that point in the far end relative to the midpoint, that angle theta, which can be figured out geometrically, right? Or is given to you for that matter. The direction, that depends again. Is it a positive or negative line charge distribution? What side of the distribution are you on? And that you just go back to thinking about, again, the individual components, and that's it. So that's a pretty good one right there. That comes in handy. So we've looked at 2 different electric fields in the vicinity of a line charge, and you may be asking, well, what if we weren't directly above the midpoint? What if we were shifted over a little bit? Well, this actually follows the same sort of logic that we had here. We would break this down into an x component and a y component. X components wouldn't completely cancel out because why? Well, because there wouldn't be symmetry anymore. So if we just said, what is the total due to this 1/2, we would have the y component was equal to, if we take away that 2, was just equal to this quantity there, j hat, and then we'd have an x component. Well, we'd have to reintegrate over, but we'd find that it ends up being much the same. We'd end up with the integral of cosine theta instead, and that would be our x component. But we start to have to be a little bit more careful with that. That's doing integration in 2 different dimensions, and then that's how we've been utilizing vectors anyway. We're not going to really go there, but if you can do this, that falls out pretty easy. All right, that was fun, right? Heck yeah, it was. So yeah, let's do a couple little problems just utilizing this, and that'll be that. So give me a second, and I will erase this up, do two little problems, and move on. Be right back. All right, so before I actually do the problem, there's one other piece of information that I want to give regarding the line charge, and the question would be, what if the line charge were infinite? What would E hat be then? And once it's infinite, it's kind of constrained to being either, well, if it's infinite in the x direction, and above or below it, infinite in the y direction, to the right or to the left, we have to be on either side of it. So what happens if it is infinite? Well, can we do anything? And what does that mean, it's infinite? Well, infinite could mean it's just an approximation, or it could mean that we're talking about, yeah, a line charge that's infinite in length, which doesn't really exist, but we can still utilize it as an approximation. So if we have something that is really long, and we'll just say it goes on to positive infinity, goes on to negative infinity, where's the midpoint? That's right, it's anywhere you want it to be because it's infinite in length. There is no well-defined midpoint, it's everywhere. So we just pick a spot and say, okay, well, it's going to be right here. That's going to be the midpoint, where again, it's arbitrary, it doesn't matter. So we're some distance a away from the line charge, short distance a away from this infinite line charge. What angles do the ends make with respect to that point? Well, when we're really close, right, the angles made are fairly small. Well, there we got theta, that looks like it's about, what, 40 degrees or something. And then we get farther away, that angle gets bigger. Now I've got something around like 60 degrees. And then we come over here, we've got something that's more like 80, 85 degrees. What happens at the end of it? It's infinitely far away. What's the angle then? So the angle, theta is equal to 90 degrees for, theta sub 0 is equal to 90 degrees for a line of infinite length. So that's what we get. It's infinitely far away and makes a 90-degree angle with respect to the end and that point. So if we go ahead and say, well, what's the electric field? We still have symmetry on either ends. The x component ends up canceling out, and we're only left with, in this orientation, a y component. And we already know that, hey, its magnitude is going to be equal to 2k sub e lambda divided by a times the sine of theta sub 0. Well, theta sub 0 is 90 degrees. What's the sine of 90? 1. Evaluated at theta sub 0 is equal to 90 degrees. Gives us that E hat for an infinite line charge is equal to 2k sub e lambda divided by a. What's interesting about that? It just varies as 1 over a. Where a is the distance away you are from that particular line charge itself. The further you are away, the weaker the field is, but it doesn't go as a squared, it just goes as a. So sometimes we'll write r here. I prefer putting r there because a is kind of a well-defined, and we could just write it as something that's variable, and we can say, hey, we could be any distance r away from it. But book uses a gets used, right here we just have a. But this is important too. The electric field due to an infinite line charge is just 2k sub e lambda over a. Boom, easy to get once we've gotten that one solution. And then in terms of its direction, that just depends. Is it a positive or negative line charge density? Are we on this side or that side? And then we go from there. All right, so let us then look at an actual problem here. And it's a short problem, but it involves the three things that we've just looked at. A continuous line charge, aligned with the ends, aligned with the midpoint, and then infinite. And just determining what the electric field is. So, here is the problem. All right, so what do we have? We've got ourselves a line charge that's laid across the x-axis, going from x is equal to 0.3 to x is equal to 0.5, and we want to know what is the electric field at the origin, above the midpoint, and then what happens if it's an infinite line charge. So let us just do this. We can have ourselves a nice little coordinate system here. Sure, we've got ourselves a y, we've got ourselves an x, and I'm going to put in our line charge here. So we're saying it is going from 0.3 to 0.5. Does that seem about right? So 0.3, 0.5, 1, 2, 3, 1, 2. That seems okay. So there's going to be our line charge. So this is 0.3, this is 0.5. And this has a line charge density of 1.7 coulombs per meter. It's not even a meter long, right? It's only 20 centimeters, but if it were a meter long, it'd have 1.7 coulombs of charge. Okay, and we've got some questions regarding this. So the first question is, what is the total charge that's contained by this? So A. Q total is equal to a what? How do we get Q total? We go back to the line charge density and the length of this line itself. We've got that lambda is equal to Q divided by L, so Q is equal to lambda times L. And in this case, L is going to be equal to that distance right there, which is 0.2 meters. Put little meters here, meters. And there we go. So we've got ourselves that Q total is going to be equal to 1.7 coulombs per meter multiplied by 0.2 meters. So there we go. What do we get out of that? We've got ourselves 0.85. 1.215. Sorry. Doing something bad. 0.34 coulombs. All right, there we go. 0.34 coulombs. Seems pretty easy. So there's the total charge that is encompassed or spread across this line of length 0.2 meters. So then we go to part B, which is a little bit more interesting, but do it. Now we want to know, what is the electric field as a magnitude and direction at the origin? Well, here's the origin right here. We want to know what is the electric field there. E hat is equal to a what? So we got to do this in two different pieces, right? Magnitude and direction. So what's the direction of the electric field at that point due to this line charge right here? So again, this is a positive line charge. We have radially outward for every infinitesimal element. Every infinitesimal element radially outward with respect to it along the x-axis on this side is that way. So we have to have that the electric field over here is pointing in the negative I hat direction. So there, we've got the direction already. Now we just get the magnitude. How do we get the magnitude? Well, we've got the magnitude at 0, 0, at 0, 0, E hat is going to be equal to, whoop, we've got an expression already. We know that it's K sub E lambda L divided by A times L plus A. So then it's just a matter of what is lambda, what is L, what is A. So what are those values there? Well, A is this distance right here. It's the distance from the point under consideration to the near end. And L is this distance here. It is the length of the line charge itself. We've got that A is going to be equal to 0.3 meters away. 0.3 meters from the origin. And L is going to be equal to 0.2 meters. So we got everything. We got lambda, we know what k sub e is, fantastic. So we can go ahead and calculate this out now and say that the magnitude of the electric field, let's not even say magnitude, we already know the direction. We'll just say that the overall electric field at 0, 0 is going to be equal to, I want to put in the negative for the I hat direction, negative k sub e times 1.7 coulombs per meter times 0.2 meters divided by the quantity of 0.3 meters multiplied by the quantity of 0.2 meters plus 0.3 meters. And then we'll go ahead and put an I hat there. Negative I hat direction, there's the magnitude. We can compute this out and we're done. We've got 8.99 e to the ninth times 1.7 times 0.2 divided by the quantity, 0.3 times 0.5, 0.3 times 0.5. And what did I do? That should be insert E. All right, let me do this. 8.99 E to the 9 times 1.7 times 0.2 divided by 0.3 times 0.5. 2.038 times 10 to the 10th. 2.038 times 10 to the 10th. What are the units? We're going to end up with newtons per meter again, as we should. Newtons per meter. Newtons per coulomb, sorry. Newtons per coulomb. Unitization of the electric field. There we go. Really strong electric field. Well, we're pretty close to a pretty big amount of charge there. There we have it. Electric field, magnitude, direction. And let me not forget, negative I hat. Ooh, almost forgot that part. That would be disastrous. All right, so now we'll ask, pertaining to the same system, what is the electric field at a distance of 0.4 meters above the midpoint of this line charge? So we can still take this, just go ahead and put out our little line charge right there. And now we're going to go 0.4 meters, that should be 0.2, 0.4. There we go. We want E hat at that point right there. So in this case, we're above the midpoint. We've got A is equal to 0.4 meters. And we've got that L is equal to 0.2 meters. Again, we're starting at 0.3 to 0.5, and we're 0.4 meters away from it, above it. And we got the same lambda here. Lambda is equal to 1.7 coulombs per meter. And there we go. What direction is the electric field going to be at that position in space, above the midpoint there? Has to be straight up, right? Yeah, that's it. It's got to be in the positive j hat direction. Because again, it's positive, everything's radially outward, the x components cancel out, we're only left with the j hat component because of the orientation of things. So then it's a matter of figuring out what else we need to know. And we've got the expression, once again, that the magnitude of the electric field aligned with the midpoint is going to be equal to 2 k sub e lambda over A. Times the sine of theta sub 0. There we go. So let us just figure out what we need. We know what lambda is, we know what A is, we just need theta sub 0. What's theta sub 0? Well, theta sub 0 is this angle right there. So let's take that out, draw it out a little bit bigger, and we've got ourselves, this is not really scaled out too nice. Like this. A little, twice as big, like this. So there is theta sub 0. Well, this here is L divided by 2. which is going to be equal to 0.1 meters, and this is 0.4 meters. So what do we get out of that? How do we get theta? Well, we get ourselves that theta sub 0 is going to be gotten by the arctangent of 0.1 divided by 0.4. And working in degrees here, let me make sure I'm in degrees, which I'm not. We've got ourselves arctangent 0.1 divided by 0.4 gives us 14.036. That sounds good. 14.036 degrees. And then we can go ahead and stick that in there and get ourselves that E hat itself is going to be equal to 2 times K sub E multiplied by 1.7 coulombs per meter divided by the distance away, which is 0.4 meters, multiplied by the sine of 14.036 degrees. And that is going to be in the positive J hat direction, which we've already determined. So we go ahead and compute this out. 2 times 8.99 times 1.7 times the sine of that last answer divided by 0.4. I get 1.853. 1.853 times 10 to the 10th newtons per coulomb, a J hat. There we go. We got ourselves the magnitude and direction of the electric field at that point. So this was a part B, right? Nope, part C, sorry about that. One last part, part D. What if it were an infinite line? This is regarding part C. So what do we do? Well, instead of this for the angle, now we have that theta sub 0 is just equal to 90 degrees. So we've got that the electric field then is still going to be in the positive J hat direction. It's just going to be 2K sub E lambda divided by A. 2K sub E times 1.7 coulombs per meter divided by 0.4 meters, which we could just take this last answer and divide it by the sine of that answer. Answer divided by the sine of 14.036. Dividing that quantity out, and we get 7.642 times 10 to the 10th. 7.642 times 10 to the 10th newtons per coulomb J hat. Quite a bit stronger if it's infinite, but that's it. All right, so these are the things you got to deal with. And what you got to be careful of is where you are relative to the line charge and how the line charge is oriented, and is it a positive or negative line charge? And that will all have to do with the overall direction. Magnitude is usually easy to work out. Directions can mess people up. And yeah. It's been fun. Hair standing on its end. All right, till next.